Part 2, Chapter 2, Introduction to Molecular Orbital Theory. Diatomic molecules of second-row elements. Diatomic molecules containing atoms of the same element. So Li2, Be2, P2, C2, and 2. So this is considered as the 1, 2, 1, 2. So this one O2, F2, and Ne2 is the 1, 2, 2, 1. Second row, 1s orbital smaller than 2s. For lithium, overlap of n is equal to 2, orbitals will be much more than 1s. Also 1s orbitals both completely fill, so both sigma and antibonding sigma molecular orbitals formed from this are filled. Therefore, no net bonding, can ignore 1s, can focus on valence electrons and orbitals. So that's why when you draw for the lithium electron configuration here, so we just draw for the molecular orbital diagram for the 2s1. We look at the valence electron. So this is the energy. So 2s, this is the atomic orbital for the lithium, and this is the molecular orbital for the Li2, and this is the atomic orbital for the Li. So 2s1 here, so 1 electron here and 1 electron here, total 2 electron. Put the electron in the lowest energy level. Molecular orbital energy diagram for Pe2. Pi to P lower in energy than sigma to P. Beryllium electron configuration equal to the helium 1s2, and this is the 2s2 for the valence electron. So this is the orbital diagram for the molecular orbital Be2 here, and this is the orbital of Be. And we know the valence electron 2s2, so 2 electrons here, and same goes here, 2 electrons. 2 plus 2 equal to 4, so you need to fill 4 electrons in the Be2 for the molecular orbital. So we need to fill the electron at the lowest energy level of the sigma to s. So only one orbital here, so 2 electrons, and another 2 will fill in the antibonding for the sigma to s. So for the bond order is equal to the bonding electron minus with the non-bonding electrons. 2 minus 2 divided by 2, so the answer is 0. If bond order is equal to 0, meaning that Be to Be no net bond, means the bond does not form. Be2 electron configuration, we need to start with the 1s. For the sigma 1s2, sigma antibonding 1s2, and sigma to s2, and another one is the sigma antibonding to s2. So for the molecular orbital, we just draw for the valence electron to s2. In terms of the magnetism, so for the Be2 is diamagnetic as no unpaired electrons or spins. So we look here, all paired, so meaning that this is the diamagnetic. For the molecular orbital energy diagram for P2, pi to P lower in energy than sigma to P. So you must remember 1, 2, 1, 2, start with the Li2, 2, N2, and O2, F2, and higher, this 1, 2 to 1. First, write the boron electron configuration. So this is the valence electron 2s2 2p1. Now because of the 2p here, so remember p2 1 2 1 2 and draw the molecular orbital. Start with the 2s2 and then 2p1. So here 2s2, so this is the atomic orbital for boron, and also here, and in the center here is for p2 for the molecular orbital. So 2s2 2p1. Follow the electron configuration of boron because this is the boron, and same here 2s2 2p1. And now for the 2s, 2 plus 2 equal 4. So fill 4 electrons in the molecular orbital of the p2. Start with the lowest energy level, sigma 2s2, another 2 for the sigma antibonding 2s, and 4 here, and 2p1, another 2p1 here, 1 plus 1 equal 2. Now fill the electron at the lowest energy level for the pi 2p. So this is how you fill in the electron. Follow the Hans rule. 4 minus 2 because for the anti-bonding electrons here, and divide by 2 is equal 1. So B to B single bond. So this is the stable molecule. So this is how we know that pi to P is lower in energy than sigma to P. So this is the lower energy than the sigma to P. For B2 electron configuration, sigma 1s2, sigma antibonding 1s2, sigma 2s2, sigma antibonding 2s2, and pi to P 2. So you just write pi to P, acceptable. Here pi to P 2. So for the magnetism is paramagnetic because has 2 unpaired spins. So look here, unpaired electrons. How many unpaired electrons? 2 unpaired electrons. So just look at the central here. So if want to identify the HOMO, so HOMO for the B2 is the pi to P. So for LUMO is sigma to P. Molecular orbital energy diagram for C2, pi to P lower in energy than sigma to P. Carbon electron configuration. So this is the valence electron 2s2 to p2, and draw the molecular orbital. So here is the 1 2 1 2 because of this C2, and carbon here is 2s2 to p2 to p2. Same goes here, carbon 2s2 to p2. So this one fully filled with the electrons, and this one 2 plus 2 equal 4. That means you need to fill 4 electrons in the pi to P orbitals. So for the bond order, 4 plus 2 is equal to 6 minus 2 and divide by 2, and the answer is 2. Carbon to carbon is double bond, so this is the stable molecule. In terms of the magnetism, C2, all this one paired electrons, so this is the diamagnetic. C2 electron configuration, sigma 1s2, sigma antibonding 1s2, and sigma 2s2, sigma antibonding 2s2, and pi to p 4. Just write the pi to p, calculate this one, electron, 4 electron. Molecular orbital energy diagram for N2, pi to p lower in energy than sigma to p. This is the electron configuration for N, nitrogen, 1s2, 2s2 to p3. This is the molecular orbital for N2. So first, draw for the 2s orbital. So this is the nitrogen 2s2 and another nitrogen 2s2. So for the sigma 2s and sigma antibonding 2s fully filled with electrons. And for the 2p3 is for the nitrogen and another nitrogen here 2p3, 3 plus 3 equals 6. And the 6 electrons fill in at the pi to p and also the sigma to p. So 4 electrons at pi to p, 2 electrons at sigma to p. So for the N2 electron configuration, start with the 1s, sigma 1s2, sigma antibonding 1s2, sigma 2s2, and sigma antibonding 2s2, pi to p 4. So this is the pi to p 4 and sigma to p 2. Bond order for N2 is equal with 8 minus 2. So here 6 plus 2 for the bonding electrons equal 8 and minus 2 for non-bonding electrons divided by 2 equal 3. So for N2, a triple bond, this is the stable molecule. For the magnetism, N2 is diamagnetic as no unpaired spins. So here we look at the central for the N2. So all paired electrons. So this is the diamagnetic. Molecular orbital energy diagram for O2, sigma to p lower in energy than pi to p. That means sigma to p here is lower in energy than pi to p. So you remember 1, 2, 2, 1. First, write the electron configuration of oxygen, which is 1s2, 2s2, and 2p4. And then draw the molecular orbital for O2. So O2 here, meaning that the atomic orbital is oxygen plus oxygen. So oxygen plus oxygen become O2. So 2s2 and 2p4 follow the electron configuration of oxygen. As for the 2s2 to p4. Same with this atomic orbital of oxygen. So for O2, 2s2 and 2s2 fully filled with the electrons. And for the 2p, 4 plus 4 electrons here equal 8. So you need to fill the 8 electrons in this molecular orbital of O2. Start with the lower in energy level for sigma to p. So because one orbital here, maximum is 2 electrons. So another 6 to fill here. So because this one only limit to 4 electrons, so another 2 at pi antibonding to p. Bond order is equal to 8 minus 4 divided by 2 because 8 here 6 for the bonding plus with the 2 equal 8 and minus 4 because of the antibonding here 2 electrons plus 2 electron equal 4 divided by 2. The answer is equal to O2 is double bond because of the bond order is equal to O2 is paramagnetic because has two unpaired spins, meaning that two unpaired electrons. So for the O2 electron configuration, sigma 1s2, sigma antibonding 1s2, sigma 2s2, sigma antibonding 2s2, to P2 here, pi to P4, pi to P4, and pi antibonding to P2. Molecular orbital energy diagram for F2, sigma to P lower in energy than pi to P. So this is the sigma to P lower in energy than pi to P. First, write the electron configuration of fluorine 1s2 to s2 to P5. So draw the molecular orbital. So fluorine here and another fluorine atom. And this is the molecular orbital for F2. 2s2 for the fluorine and 2p5. And same goes here. Now this is the fully filled with the electron. So 5 plus 5 equal 10 electron in this molecular orbital. Start at sigma to P, pi to P 4 electrons, and another 4 electrons at pi antibonding to P. So bond order for F2 is equal to 8 minus 6 and divide by 2. Because of 8 bonding electrons, 6 plus 2, and minus 6 because of the 4 here, non-bonding electrons plus with the 2 non-bonding electrons equal to 6 divided by 2. The answer is 1. F2 a single bond, and for the magnetism is diamagnetic as no unpaired spins or unpaired electrons. F2 electron configuration, sigma 1s2, sigma antibonding 1s2, sigma 2s2, sigma antibonding 2s2, sigma to P2, pi to P4, and pi antibonding to P4 because of the 4 electrons here. Molecular orbital energy diagram for Ne2, sigma to P lower in energy than pi to P. This is the electron configuration for Ne. So the valence electron to s2 to P6. And you need to draw the molecular orbital for Ne2. So for the bond order, 8 minus 8 because of 6 for the bonding electrons plus another 2 electrons equal to 8, and you minus with the 6 here antibonding plus with another 2 electrons at antibonding orbitals, and divide by 2 is equal to 0, meaning that Ne2 no net bond, that means does not form. Magnetism is diamagnetic as no unpaired spins. And for the Ne2 electron configuration, sigma 1s2, sigma antibonding 1s2, sigma 2s2, sigma antibonding 2s2, sigma to P2, pi to P4, pi antibonding to P4, and sigma antibonding to P2. And we see all the orbitals fully filled with the electrons. Using molecular orbital theory to explain bond properties, this is the molecular orbital of N2. This is the molecular orbital for N2 positive 1. N2 forms N2 positive, bond order decrease. So from 3 to 2.5, N2 positive has a weaker, longer bond than N2. So when you look at the N2 positive, meaning that lose 1 electron. So here is only 1 electron compared to N2, 2 electrons at sigma to P. O2 and O2 positive, O2 forms O2 positive bond order increase from 2 to 2.5. O2 positive has a stronger, shorter bond than O2. So here O2 positive lost one electron. So here missing one electron compared to the O2, 2 electrons at pi antibonding to P. Try this exercise for F2 and F2 negative 1. We done chapter 2. Thank you.